Global digital communication across the modern internet requires exact mathematical coordinates for every single piece of data in transit. When we look at an IPv4 address, it is commonly misread as a single static identifier, a simple label for a single machine. In reality, an IPv4 address is a dynamic 32-bit hierarchical structure. This diagram illustrates that structure, splitting the 32-bit address into two distinct halves, a network portion on the left and a host portion on the right. This establishes the foundational rule of local communication. If two devices share identical bits in this Navy network portion, they physically reside on the exact same local network. Conversely, the teal host portion must remain completely unique to every single device on that specific network to avoid a collision. But there is a mechanical problem. By simply looking at a 32-bit number, the computer itself cannot determine where the split between the network and the host occurs. The IP address is structurally blind. It relies on a secondary metric to locate that boundary. That boundary is provided by the subnet mask. You can see this mechanism directly in a standard Windows configuration dialog box. An operating system will refuse to assign an IPv4 address to a host unless a corresponding subnet mask is provided alongside it. These dotted decimal numbers are the literal blueprint for how the machine perceives the outside world. Devices do not infer or guess their network boundaries based on decimal values. Network hardware must strip these decimals down into raw binary to function. Once converted to ones and zeros, the processor executes a ruthless bit-by-bit calculation against both the IP and the mask to discover exactly where its home network begins. This diagram demonstrates that calculation using a foundational Boolean operation known as logical AND. The core rule of logical AND is strict. A 1 and a 1 equals 1. Any combination involving a 0 forces the result to 0. Walking through the vertical calculation, wherever the subnet mask has a 1, the IP address bit drops directly down into the result. But wherever the mask has a 0, the output is unconditionally forced to 0, masking out the host bits entirely. The final result of this operation is the exact network address. Because of how this math functions, the numbers that can actually appear in a subnet mask are severely limited. This reference strip outlines those limitations. Because subnet masks barrow bits sequentially some left to right, the octets cannot be random numbers. These 9 specific values, from 0 to 255, are the only mathematical building blocks allowed in any subnet mask octet. To write this out efficiently, engineers use prefix length or slash notation. A /24 simply dictates that there are 24 1 bits counted consecutively in the subnet mask. This binary math carves out a highly specific, finite block of IP space dedicated strictly to a given local network. This number line illustrates the 3 distinct address types contained within every carved-out subnet block. At the far left is the network address. It contains all zeros in the host portion and cannot be assigned to any device. At the far right is the broadcast address. It contains all ones in the host portion, and it is also unassignable. Only the span sitting strictly between these two endpoints contains valid, usable IP addresses for host devices. Understanding the structure of these addresses reveals exactly how devices transmit data between them. This one-to-one diagram demonstrates unicast transmission. Unicast is an efficient, targeted communication where the destination IP is a single recipient on the network. Contrast this with multicast, which sends a single packet only to a specifically subscribed group of devices, a method heavily used by routing protocols. Unicast and multicast are targeted and efficient. However, networks are legally required by protocols like ARP and DHCP to support a third, highly destructive type of transmission. This is the broadcast transmission, a one-to-all message directed exclusively at that unassignable all ones address at the end of the subnet block. A broadcast transmission acts as an unavoidable physical ripple across the entire local network environment, affecting every single machine. Looking at this switch diagram, we see how standard network hardware reacts to this ripple. A switch is engineered to flood a broadcast frame out of every single active port, except the one it arrived on. Every device that receives this frame is forced to pause its operations, interrupt its CPU, and process the packet. As more hosts are added to a single unsegmented switch, the broadcast volume grows exponentially. Massive, flat networks eventually choke on their own localized broadcast traffic. This obliterates performance and makes enforcing security policies physically impossible. The engineering solution to the broadcast storm is network segmentation through subnetting. Here is a failing, unsegmented environment overwhelmed by traffic. Introducing a router into the center physically splits the hosts into two distinct pools. When a broadcast pulse initiates on the left, it hits the router interface and is instantly deleted. It does not cross over. This illustrates the cardinal rule of Layer 3 boundaries. Routers do not forward broadcast traffic. Subnetting effectively shrinks the broadcast domain, containing the noise to smaller, manageable segments. Subdividing a physical space through logical subnet calculations restores network performance and allows engineers to enforce strict access rules between departments. There is one major caveat to this architecture. The IP addresses we meticulously segment for our internal networks are almost entirely RFC 1918 private addresses. Private addresses are reserved strictly for internal organizational use. They are completely non-routable on the global internet. If an ISP router receives a private address, it drops the packet immediately. This diagram shows how internal networks bridge the gap to the outside world. Using network address translation, the edge router intercepts an outgoing packet and strips its private source IP. The router replaces it with a globally unique public IP before sending it to the internet. This translation allows hundreds of internal devices to securely share a single public IP address. Subnetting mathematically organizes and protects the local environment, while NAT provides the gateway for those isolated machines to participate in global communication.